Right, yes, so thank you very much. Thanks to all the organizers for putting together this very nice conference. And also thanks to all of you for sticking around until the very end. And we started this week by a talk on finite temperature phases of matter. So fittingly, I will end it by another talk, with another talk on finite temperature phases of matter. And this is work done together with this set of people, in particular Benedict, who's a postdoc in Oxford, has played a major part. And I'll start with the principle. Well, I was trying to use my own, but let's see. No, it's fixed. It's magically fixed. Okay, so I'll start with the punchline, just in case I don't get to the end, which is the following. So we propose a definition for a new phase of matter at finite temperatures. And the defining property of this new phase is that it combines features we associate with topological order, things like long-range entanglement, with features that appear in various models of classical spin glasses. And I will give kind of increasingly precise definitions as I go along of what I mean by this. And we show that this phase is realized in some family of models which are based on certain quantum error correcting codes. And the catch is that these involve some long-range interactions, which is not so surprising. Coming from the direction of spin glasses, they are a bit similar to various models of mean-field spin glasses that involve long-range interactions. And finally, a sort of a separate thing that connects to this, but also is interesting on its own right, we kind of prove a theorem on properties of quantum channels, which is relevant for understanding what happens when you couple these things to a bath, basically showing sufficient conditions for a quantum channel to get stuck near certain initial states. So if you're here for Angela's talk on Tuesday, this is kind of a complementary result. She was talking about sufficient conditions for channels to mix very quickly. This is a condition for channels that they are not able to mix very quickly. Okay, so I'll be talking about finite temperature phases, and just to sort of situate what I'll talk about, where it fits into these phases. So the simplest example you might think of a finite temperature phase is something like the Ising model, which has spontaneous breaking of a discrete Z2 symmetry. So you have two kind of macroscopically distinct equilibrium states distinguished by a local order parameter. And you should contrast this with ideas of topological order. And since something about finite temperature, the simplest example would be in 4 dimensions, a 4D toric code, which has a finite temperature version of topological order, where you still have kind of distinct equilibrium states, but they are not distinguished by local order parameters. On the other hand, they have some other features that make them non-trivial, in particular, some long-range entanglement. And kind of another related perspective you can take in this distinction is in terms of the ability of these systems to serve as a memory, to encode some information. So in the classical Ising model, you can use it to encode 1 bit of memory as a kind of magnetic hard drive. If I initialize a state with a positive magnetization, this will be preserved up to some exponentially long time. And similarly, the 4D toric code is able to preserve quantum information coherently up to some exponentially long time. But other than this sort of classical symmetry breaking, in the classical case, there's another mechanism for preserving information, which shows up in certain models of spin glasses. But the idea is that you have some very sort of complicated, rugged energy landscape with lots of local minima. And each of these local minima is some stable configuration that can preserve some memory. If I have a particular initial state corresponding to a minimum, I'll stay near that configuration for a long time. So once I set things up this way, there's kind of an obvious missing box here, and this is where we come in by proposing what we call a topological quantum spin glass, which kind of has both of these features. It has this sort of complicated landscape, but the local minima, instead of corresponding to classical configurations, they correspond to kind of highly entangled quantum states, which actually can be used to preserve quantum information. So this is kind of the short version, and now I'll kind of go into more detail and explain how to actually define these various things, and then how to realize in a concrete example. But just to state more explicitly, so the set of features we are looking for is a combination of a kind of what people call a complexity of the landscape, of the energy landscape in spin glasses. There are many of these minima that are stable at finite temperature, and most of them are kind of local minima and not global minima. And also a kind of quantum complexity, which is that it can serve as a quantum memory, and these states are long-range entangled. So how to actually define this in some slightly more precise way? What does it mean for a finite temperature state to be non-trivial? Going back to the Ising model as an example, one way of thinking about what happens at low temperatures, which will generalize nicely the cases I care about, is that as I go below the critical temperature of the Ising model, the Gibbs state, e to the minus beta h, kind of becomes bimodal. It fragments into two components. It has large probability for positive magnetizations and large probability for negative magnetizations, and very small probability for states with near zero magnetization. Okay? So now we'll try to generalize this idea to give a definition of what it means for a finite temperature state to be non-trivial. And the idea is the following. So now I want to do this in Hilbert space for a quantum system. And what I do is I take some subspace of the Hilbert space, which will host kind of one of these components. And for each subspace, I want to define a boundary in Hilbert space, which is given by all the states that I can obtain by taking a state in the subspace V and then acting with some local operators. Okay, so these are states in the many-body Hilbert space, which are in some sense close to the starting subspace, that I can get them by just doing some local operations. And in practice, I have to put in some number of how local these operations are, and I will take that to infinity when I take the thermodynamic limit. And what I want is that the probability associated in the Gibbs states to this subspace should be much larger than the probability associated to its boundary. So it should be something like this, where there is some region with a large probability surrounded by a region of very low probability. And if this holds, I'm going to say that this subspace hosts kind of a component of the Gibbs state. And in a non-trivial phase, there will be multiple such components. The Gibbs state sort of fragments into multiple components in Hilbert space. So why is this a useful definition? And this is where kind of a dynamical perspective is useful. So we can ask, what happens if I couple the system to a bath? The bath we can model by some quantum channel, which has the property that it has the Gibbs state as its steady state. If I wait for long enough, eventually the bath will thermalize the system to the Gibbs state. And let us assume that the Krauss operators associated to this channel are local in space. So in this paper, we proved the following theorem about the setup, that let me take the Gibbs state and project it down to one of these subspaces and ask what happens to it if I evolve it for sort of one time step. Apply the channel to it and ask how much does it change? How big is the time derivative? And we can upper bound this time derivative with a ratio that depends only on the probabilities associated to the boundary and the probability of the subspace itself. If this ratio is sufficiently small, the time derivative is small, then if I initialize the system in the subspace, it will get stuck there for a very long time. And this is a generalization of kind of a well-known result about classical Markov processes. You can have these kind of bottlenecks in classical Markov processes that prevent you from thermalizing quickly. But we were able to prove a version that generalizes to quantum channels. There is one sort of weird-looking thing about this formula, which is the square root. Like, why is there a square root here? In the classical version, it's just a ratio of probabilities. But it turns out that because in the quantum case, your Gibbs state might have off-diagonal matrix elements, you need to bound those off-diagonal matrix elements. And when you do that, you end up with this extra square root compared to the classical case. Yeah.
When you say
well, so in the definition, which I sort of on purpose didn't find out in detail, but imagine taking a state from this subspace and acting on it with any operator which is at most R local or for some number R. and then take the superposition of all of those. And then the claim is that if the Krauss operators are also at most R local, then this holds. So there are two places where locality enters. One is the definition of the boundary, the other one is the locality of the channel, and those kind of have to match. Yeah, exactly. So yeah, so it's not including the ones that are in V. Exactly. So what you could imagine is this channel might be something like e to the L for some order one time. And then you would have some small tails kind of leaking out. And then you would get some errors, but those would be suppressed. You can kind of slightly modify it, or you can ask what happens if this locality is approximate, and then you can put in some extra errors in the theorem. Okay, so what this theorem tells you is that, and there is a physical picture that you can think of this as kind of free energy barriers, that in order to leave this subspace, there is some big free energy barrier that I have to go through, and that's why I get stuck there. And now this gives you a condition explaining why, when this ratio is small, if it goes to 0 in the thermodynamic limit, you should really think of each of these subspaces as kind of a separate component of the Gibbs state, similar to what happens in the Ising model. So basically, the approach we'll take is we define this as a way of decomposing the Gibbs state into many components, and different phases will be distinguished by how many such components there are and what other properties these components can have. So in particular, given this definition, you can make a distinction between classical and quantum phases. And one way you might do that is by asking whether the system preserves classical or quantum memory. So whenever I have more than one component, as defined in the previous slide, the system has some sort of memory. There are different initial states I can start in, and I stay there for a very long time. So there's some memory of the initial state that I preserve. But the question is, what is the structure of this memory? Is it only classical, or can I kind of coherently preserve some quantum information? And this is encoded in the structure of these different Gibbs state components. So if I look at all the possible components, in a classical system like the Ising model, it's just kind of a classical mixture of a few extremal states, that I have these two components with different magnetizations, and then I can assign different probabilities to them. So that's isomorphic to just having a classical bit. So it's encoding one bit of classical information. But if I look at something like the 4D toric code, then the structure of Gibbs states look different. It kind of has roughly this structure, where it looks like an arbitrary 2x2 density matrix tensored with some junk. But the main point is that the set of all the possible Gibbs states is isomorphic to the state of a qubit, so that you can kind of use it to coherently preserve quantum information. So that's one distinction you can make, is basically different structures of how you can decompose the Gibbs state. In the classical case, there is only one way of decomposing it. In the quantum case, there are kind of different ways of decomposing it, kind of corresponding to the X basis or the Z basis of this qubit. There's another distinction you can make between classical and quantum, which is in terms of entanglement, asking whether these components of the Gibbs state have some sort of long-range entanglement. And you can define it as follows. So for pure states, there is a usual definition of short-range entangled states as those that you can create from a product state with some finite time evolution or with a finite depth circuit. And for a mixed state, you say it's short-range entangled if it's a mixture of such short-range entangled pure states, and it's long-range entangled if it's not written as such. You could also distinguish classical and quantum by whether these Gibbs state components have long-range entanglement in this sense. And one kind of interesting point, which relates to Kurt's talk on Monday, is that these two notions of quantumness, they often come together. In the 4D toric code, you have both, but they don't have to come together. So in the example that Kurt talked about on Monday, you have the second notion of quantumness, but you don't have the first one, which is kind of interesting on its own. So this is distinguishing classical from quantum. The other thing we want to distinguish is something that's more like symmetry breaking order in the Ising model versus this glassiness that shows up in these other models I'll think about. In the Ising model, there's only two of these Gibbs state components, and they are related to each other by global symmetry. But in spin glasses, and the standard example is something like the Sherrington-Kirkpatrick model, which is an all-to-all Ising model with random coefficients, you end up with a different scenario where you have lots of different components of the Gibbs state. There are lots of different subspaces satisfying that definition I gave. In fact, their number grows with the system size. And these different states, they are not all related to each other by symmetry, which you can already see by the fact that they can have different energies. And indeed, lots of these components, they don't contain any ground states. They kind of only contain high energy states. So as you go higher up in energy, you get more and more of these. There is some non-trivial temperature dependence. So this gives us kind of following classification of different phases. So we are decomposing the Hilbert space into these subspaces defined by properties of the Gibbs state, where it's concentrated. And you can ask, can we use this to preserve quantum information? Do the components of the Gibbs state have long-range entanglement? And I can also ask about the number of these components, and also whether there are components that don't contain any ground states, that are kind of these only contain high energy states. And what we show is that there exist some models where the answer to all of these questions is yes. You both have these quantum properties, and you also have many stable minima, which comes with these glassy features. And these are the so-called, what we call topological quantum spin glasses. Okay? And the examples that we construct are all based on certain quantum error correcting codes. So for the rest of the talk, I'll explain a little bit how this construction goes. And the general logic of the construction is the following, that for quantum error correcting codes, there are various nice constructions of constructing them out of classical error correcting codes. So classical error correcting codes have been studied a lot more. There's a lot known about them. In particular, it's known that many classical error correcting codes already have features of classical spin glasses, although we give a slightly new perspective on this property. But there is some property of classical error correcting codes, which we call linear confinement, that guarantees that they have this sort of glassy feature of having many local minima that are stable at finite temperatures. And then we use various methods from the theory of error correcting codes, take these classical codes and turn them into quantum error correcting codes. These go by the name of various product constructions. And the key point is that, on the one hand, going from classical to quantum codes gives rise to these quantum features, having a quantum memory and long-range entanglement, but you also preserve all the glassy features that you had in the classical codes that you started from. That's the general logic. And because of this, I will talk quite a bit about the classical codes, how they work, and then it just sort of carries over to the quantum case. So what is a classical error correcting code? So I have a system of n physical bits or spins, and out of the 2n possible configurations, I want to pick out some subset, which will be my code words that I use to encode information. And physically, you can think of these as ground states of some classical model. So I associate some classical statistical mechanics model to my code, whose ground states are the code words. And you do this by assigning some kind of parity checks. You take some subset of the bits, and you want their total parity, the product of the spin variables, to be +1. So I just define that product to be a term in the Hamiltonian, and if I sum over all of them with a minus sign, then the ground states will be the configuration that satisfy all of these constraints. In the Ising model, these are just the Ising indirections, ZZ, that force spins to point in the same direction. And in the Ising model, there's only two states which satisfy all of those constraints. But more generally, the constraint might contain more spins. It might be a product of many spins. And correspondingly, there might be many different states which satisfy all the constraints, which means I can encode more information. And one restriction that we want is we want to preserve some sort of locality. So these models might not be local in any finite dimension, but they have some restriction in terms of locality, which goes by the name of low density parity checks, or LDPC, which is to say that all of these checks should contain a finite number of bits, And also, each bit should be contained in finitely many of the checks. Okay, so they are not necessarily local in real space, but you can usually picture them as being local on some graph. For example, this is a nice locally tree-like graph. You just saw some of those in the last talk. And these locally tree-like graphs often have useful properties for these kind of codes. And there's a general construction where you start with some graph, you place your degrees of freedom on the edges of the graph, and then you associate the interactions to the vertices of the graph to construct a model. And the model is usually characterized by these three numbers, n, k, and d. N is the number of bits. K is the number of encoded bits, which is to say that the ground state degeneracy is 2 to the k. And there's a number d called the code distance, which is the smallest number of spin flips that can take me from one ground state to another ground state. And this is related to how robustly I'm encoding the information. The bigger d is, the more resistant I am to noise. And in particular, people often like the sort of optimal case, known as a good code, where both k and d scale linearly with the number of degrees of freedom. So there's a finite rate, the encoding ratio of encoded to physical bits is finite, and I need to flip a finite fraction of all the bits to connect two ground states to each other. And to get such a good code, you actually need to go beyond finite dimensions. You need your model to live on some expander graph like this, which has the property that boundaries and volumes kind of scale proportionally to each other. That's what allows you to sort of break certain constraints that exist in finite dimensions. So from our perspective, we want to understand some of the finite temperature properties of these classical submech models. And in particular, we want to understand what is the energy landscape associated to them. And it turns out that for many of these codes, there's kind of a nice feature that allows to prove various properties, which goes by the name of linear confinement, which is to say that if I start in a ground state and start flipping spins one by one and ask how does the energy grow, it turns out that the energy grows linearly with the number of spins I flipped. And it continues going up linearly all the way until I flip some finite fraction of all my spins. There's a very kind of strong linearly growing energy barrier around the ground states, which is different from what you would get in finite dimensions in, say, the Ising model, where the energy cost is kind of always bounded by the size of the boundary that grows sublinearly with the size of the domain. So this is kind of specific to this expander graph context. And there's kind of a nice mathematical way of writing it, which is I can represent my spin configurations as binary vectors. It's a vector of zeros and ones, where I put a 0 if the spin is pointing up and the 1 if the spin is pointing down. And the energy is actually linear in this vector. So you can often write things as kind of doing linear operations on these vectors. In particular, I can define some binary matrix, which, given such a vector, gives me another binary vector, which tells me which terms in the Hamiltonian are excited in this particular state. And the energy is just the length of this vector. Okay, and this confinement is characterized by two numbers, delta and gamma. Delta is how far I can go before the energy can start coming down, and gamma is sort of the slope of this linearly growing barrier. And there's sort of a physical picture of why you have this, which is that, let's say you flip a spin, you create some excitations, now you flip some more spins trying to remove them, but you kind of inevitably end up creating more excitations in the process. And on this expanding geometry, you basically end up covering like a finite fraction of the whole graph before you can end up kind of re-annihilating them and going down in energy. And this confinement immediately tells you that if I restrict to some subspace or subset of configurations near ground state, at low enough temperature, this will satisfy this kind of bottleneck condition I wanted, and I will get stuck there if I try to do, let's say, Monte Carlo on this model. And that's just because if the energy grows up linearly, the kind of total probability, each of the states up here has exponentially small probability at finite temperature. So even if there is exponentially many of them, the entropy cannot win over the energy. The total probability of this sort of boundary region will still be exponentially suppressed compared to the probability of the blue region down here. So in these models, each ground state at low temperature is going to host one of these Gibbs state components. At low temperature, the Gibbs state sort of fragments into these many different components, at least 2 to the k, which is the number of ground states. But these are all still just related to ground states. You also want to know, are there any other components which are not related to the ground states, but involve kind of highly excited, high energy states? And the answer turns out to be yes. So there is a few lines of algebra that you can do, basically using this fact that the energy is linear in this kind of binary vector representation, that you can massage this linear confinement condition to show that actually for any 2 states which are close to each other, that you can get from one to the other by flipping less than delta n spins, the energy difference between the 2 is lower bounded by something that's proportional to their Hamming distance, the number of spin lifts, minus 2 times the energy of one of these. And then the key point is that, let's say I choose this reference state X to have low energy density below some finite number, then when I look at this bound, it turns out at some intermediate point, the energy has to go up by something that's proportional to the system size. I start in an arbitrary low energy state. I start flipping spins, and at some point, I have to encounter a large barrier that's proportional to the system size before I can get to, let's say, one of the ground states. And this is true for any low energy state. And then there is kind of a simple counting argument that you can do to show that not all of those can be near the ground states. There is not enough ground states to cover all of these. So in fact, the landscape must look something like this, where you have your ground states, but there's a bunch of other local minima of the energy separated from each other by large barriers. Okay, and this is exactly this kind of glassy feature that we're after. So this happens in the classical models, and now, as I said, what we want to do is basically bootstrap from this and build quantum models out of this with similar properties. So in a quantum code, it's somewhat similar to a classical code, except now you have 2 different types of terms, one involving products of Pauli Z's and the other one involving products of Pauli X's, which you need to counter all the fact that in a quantum code there are more types of noises that you want to protect against. There is spin flip noise and there is also phase flip noise. But these still all commute with each other. So I'm thinking about codes where these terms all commute. And similarly, we can describe them by the set of numbers of physical bits, encoded bits, which is the logarithm of the ground state degeneracy, and the code distance, where now the code distance also, there are 2 types of code distances. I could act with some product of Pauli X's or a product of Pauli Z's to take me from a ground state to another, and I get 2 different types of distances, and this D is the minimum of the 2, the smallest operator that can connect 2 ground states. And while in the classical case, it's been known for a long time how to construct these good codes, which have these optimal scaling of both K and D being linear in the number of degrees of freedom. In the quantum case, this is only in the last few years that people came up with constructions that can actually achieve this. Okay, and again, just like in the classical case, they involve some complicated looking geometries, which this sketch is supposed to illustrate. There's still some notion of expansion. It's not finite dimensional. But in order to define a quantum code, you also need some notion of plaquettes. So it's not just a graph, but it's some higher dimensional version of a graph that has plaquettes, not just vertices and edges. And this is just a sort of one slide aside that, these things look complicated and maybe somewhat too exotic, but they're not completely irrelevant experimentally, as we heard in Julia's talk, for example, that there are various platforms that kind of push the boundaries on trying to construct quantum many-body states where you have spatially non-local interactions between your particles, either in Rydberg atoms or a few other different platforms. So it's also sort of timely and interesting to try to explore what kind of physics you can get in these systems. And as I said, the logic is that now, since we have these classical codes, which have these interesting glassy properties, we want to use those as building blocks for constructing quantum codes. And there are various constructions that achieve this. Actually, those were the constructions, or some of those constructions, what were used to construct these good quantum LDPC codes. But what I'll describe here is the simplest of these constructions, which doesn't give you a good code, but is still interesting enough for our purposes. And it goes by the name of hypergraph product. And the idea is that it's a construction where you can take two classical codes and it spits out a quantum code. And the simplest example is that you can take as your classical code a one-dimensional classical Ising model, which you can think of as a repetition code. You can encoding one bit in the all up or all down states of a 1D spin chain. And you take two of these classical 1D Ising models, and what the construction spits out is a two-dimensional toric code. It sort of goes up in dimension by one. And I won't describe exactly how this goes, but the basic idea is that you sort of imagine taking many copies of these 1D chains, and you couple them in a particular way. So it's a little bit like a kind of coupled layer construction that you can generalize to any input. You can take any two classical codes, and then you basically take many layers of one of those codes and use some information from the other code to tell you how to couple them. And then at the end result, you end up with this kind of effectively 2D looking like thing, but it's important to emphasize that it's only 2D in some abstract representation. It's not local necessarily in 2 dimensions. In particular, if I use as my input some of these complicated expander graph codes, then what this product construction spits out is a quantum code, which again lives on some complicated non-local geometry. But it inherits properties from the classical codes in a controlled way. Okay, so this is the logic of basically what we show, is that you take a classical code, which has all these glassy properties that I discussed, you use a product construction to get a quantum code, and then basically you can show that it inherits the appropriate glassy properties, that it still has many of these local minima. But because you went from classical to quantum, it also has some of the properties you associate to quantum codes. It encodes quantum information. And in particular, each of these local minima is associated to highly entangled states. Basically, if you look at the subspace of states near one of these minima, it only contains states which have long-range entanglement. How much more time we have? Check. Okay, very good. I think that's enough. Okay, so this is the general logic. And there is one kind of trick, or one difficulty that you have to overcome when you do this, which makes the quantum case slightly more complicated than the classical one, which is that the quantum model inherits this sort of linear energy growth near the minima that you had in the classical model. But these linear barriers, they no longer go up to something that's proportional to the system size. They only go up to something that scales with the square root of the system size. This is related to the fact that in the toric code, your operators that connect the ground states, they only have to wrap around the torus in one direction and not both. So that's why you have something that sort of only goes the square root of the number of degrees of freedom rather than linearly. You have something similar in this more general case as well. There's a linear growth, but it stops at square root of the system size. And what this implies is that when you define these subspaces, you have to be a bit more careful. In the classical case, you can just take your subspace as like everything that's close to one of the minima, close defined in terms of Hamming distance, of like how many spins you need to flip. In the quantum case, you have to take a more refined definition of how to define these subspaces. Basically, you want to decompose some state into some reference state corresponding to a local minimum and some errors on top of that reference state. And you want to form a subspace, which are all the states where these errors, they don't form, there can be many errors, but they should be sparse. They shouldn't form like large connected clusters, or even a large kind of almost connected cluster. So your subspace is formed by all states where the error is sort of sparse. And the picture you should have, this is the kind of thing that you have in something like a Peierls argument, that like, if I think about what does the low temperature state look like in the Ising model in terms of like domain wall configurations? There are lots of domain walls, but they're all small. There are no like big domain walls in the system at low temperatures. This is generalizing that idea, basically. And once you do that, you use the appropriate definition. What we can prove is that in a family of error-correcting codes based on this hypergraph construction, this bottleneck ratio dimension is exponentially small, not in the system size, but in the square root of the system size. But it still goes to 0 very quickly in the thermodynamic limit. And you can come up with a similar counting argument as in the classical case to show that there are a lot more local minima than global minima in the system. Okay, so this shows that indeed you have this sort of glassy features in the quantum code as well. And this is reinforced by numerics. So because these are all commuting models, you can kind of efficiently still do some numerics on them. I mean, in some ways different, in some ways not. It's much smaller, but it's still very small. It still goes to 0, like a stretched exponential in system size rather than a straight exponential. I mean, you would also have this kind of square root in something like a 2D Ising model. It's also, the bottleneck would also be e to the minus L, which is e to the minus square root of L squared, which is the system size. It's similar. It's a little bit similar to that in that sense.
Not what you're doing.
Oh no.
So now you switch to tensor product.
Yeah, exactly. So that was just illustrating this concept. But the point is that there's kind of a black box. You could feed two arbitrary classical codes, and it spits out a quantum code.
So both of them are like this glass in a sense of case.
Yeah, exactly. It's some non-local model built from non-local classical models. Yeah. Okay. So if you do some numerics on this problem, you sort of see this glassy behavior. In particular, you see two things. So one thing that you see is if you start in a ground state and you start slowly heating it up, then you get stuck near the ground state for a long time, and there's some critical temperature where you sort of jump up in energy density. So in this regime, this ground state is kind of stable, and you stay localized near the ground state. The other thing that you see is that if you now start cooling the system back down to low temperatures, you actually go through this point. It doesn't jump down. It sort of smoothly goes through. But then it gets stuck later at some lower temperature. The energy density doesn't go down anymore, but it gets stuck at some finite energy density above the ground state. So what it shows you, the second thing, is that you get stuck in some local minimum corresponding to finite energy density, and you cannot anneal down to lower temperatures. You cannot go down to zero energy or the minimum energy, no matter kind of how slowly you go. You would have to go kind of exponentially slowly, as you expect in a glass. And the numerics shows that there is sort of two distinct transitions, which in this picture corresponds to at high enough temperature, there's just one component of the Gibbs state. At very low temperature, there are lots of components, each of which are small, but it seems like there is some intermediate regime where you have one large component and lots of small ones as well. That's kind of between these two temperatures. That's beyond our analytical proof. This is something that we just see numerically. And so far, I argued that it has this glassy property as a system, that there is many minima. But now the question is, what are the properties of this minima? How is it different from the classical spin glass? And it's different in two ways. One is the more obvious, that because it's built from a quantum error correcting code, you can use this system to encode quantum information, even at finite temperatures. In particular, the picture that we have is that you have this complicated energy landscape with lots of minima, but this landscape exists in kind of 2 to the k copies, because you can use some logical operator for classical code, something that exactly commutes with the Hamiltonian to go from one sector to another. So usually that takes you from one ground state to a different ground state, but you can use the same operators to go from one local minima to another local minimum at the same energy. Sort of everything comes in these 2 to the k copies. And now you could take any minimum and take these 2 to the k partners and use that to form a code that you use to encode information. So the point is that this is obvious for the ground states, which is what you usually do, but you could do the same thing for all these local minima involving high energy states. So you end up with lots of different copies of the same quantum code. So if you look at kind of what is the structure of the Gibbs states, most generally you end up with something like this, which is kind of a mixture between a classical and a quantum memory, that you have kind of many copies of the same quantum code, which you can parameterize by some 2 to the k by 2 to the k density matrix, but you can also have classical probabilities that you can assign for these different copies. So you can both encode quantum and classical information. It's a kind of hybrid memory that has this sort of block diagonal structure that you have many blocks, each of which is big, but you also assign classical probabilities to the different blocks. So that's one thing that makes it different from the classical glasses, where you would only have, this thing would be fully diagonal, and you would only be able to encode classical information. The other property that makes it different from a classical code is this long-range entanglement that I mentioned. So the claim is that if I look at one of these local minima at low enough temperatures, it's made out, the corresponding subspace is made out entirely by states which have long-range entanglement. In this definition of long-range entanglement, that they cannot be prepared by a finite depth circuit from a product state. And the sketch of the argument of how we prove this is based on a result in a recent work by Bravi and Yoshida, which shows that if you have a quantum code where k is proportional to n, and the code distance is at least logarithmic in n, then the states making up this code have to be long-range entangled. And now what we show is that if you take one of these subspaces and you pick an arbitrary state from the subspace, you can find kind of partner states in these 2 to the k copies of this subspace related by the logical operators of the code, such that these also form a code with a code distance that's similar to the code distance of the original code due to the fact that these subspaces are kind of small. They don't go far in Hamming distance or in Pauli weight. And since you can take an arbitrary state and form a code out of it, by this theorem, this initial state must have been long-range entangled. And since the initial state was arbitrary, this means that all the states in these sort of low-energy subspaces or low-temperature subspaces are long-range entangled. Another way of saying this is that if you took a pure state from the Gibbs distribution, like you sampled pure states from the measure e to the minus beta h for this Hamiltonian at low temperatures, with probability 1 in the thermodynamic limit, the state you sample is long-range entangled, which is much stronger than usual finite temperature topological order. So this is not something that would be true in something like the 4D toric code. Okay, so this brings me to the end. The point is that in this set of models that we considered, we proved that all these different properties kind of coexist. You have many stable minima, most of which are containing only high energy states, no ground states. They have only long-range entangled states in them, and you can use them to encode quantum information. And let me just close by saying a few words about open questions. So one is that this is one particular example where this kind of topological glassiness shows up, but there might be other models where you have similar features. Just like classical glassiness shows up all over the place in all sorts of computational problems, constraint satisfaction problems, and so on. There might be similar things when you think about quantum versions of those. Another question is, what happens in finite dimensions? So here I was talking about this kind of infinite dimensional, long-range interacting versions of mean field glasses. Even in the classical case, it's sort of a lot of debate over how much of these mean field glassy properties apply to finite dimensional glasses. When you have finite dimensions, but you have disorder, you also have glassy systems. Are they glassy in the same way or not? But at least there is some hope that some of these things that we say could actually apply to just finite dimensional disorder systems. And the last point is that, okay, we gave a definition here, but it's not necessarily a definition that's easy to diagnose in practice. It would be nice to have something that looks a bit more like an order parameter. So, of course, usual local order parameters wouldn't work, but both for spin glasses and for topological order, you have some kind of order parameter like quantities. For example, Frank mentioned Federhagen Marku as a kind of order parameter for topological order. There is sort of Edwards-Anderson type order parameters for spin glasses. So can you combine these? Can you get something like this that would be like an order parameter for these phases? So yeah, that's all I had, and thank you for your attention.